Hello. Good evening, everyone.
Good evening, sir.
Yeah.
Good
Now
evening.
let's start. I don't know. The attendance is too low. Is it because it's like second or second day of after the quiz, or what is it? Okay.
So
How
I
was
have
your?
one question.
Yeah. Yeah. Yes. Is it?
It's good, sir. Sir, in maximum likelihood, we have to take the log likelihood, right? So it should be log base 10 or it should be log base E.
Both is fine. Log base 10, log base e, both should be giving you the same result.
But there is a question in the quiz we got yesterday. So in that, the estimator, maximum MLE estimator is depend on the value of log xi, summation of log xi. So if we take ln of the points or if we take log of the points, then the answer should be vary. One answer will be 1.4 something, another one will be 2.5.
So whether that log value is provided to you?
No, sir. It doesn't mention
No,
which
sir.
one we have to take.
Okay, no issues, no issues. We'll take care of that. Till now, we didn't get the scores and all. So once we get right, the once you I get the responses from your side, we'll give the appropriate marks. If it is not mentioned, I think we thought of mentioning
Yeah.
it, but it was not.
Actually, I was thinking to use ln because natural log is used for mathematical calculation. But the professor, Arun sir, used log. So log means log, sir. And so log means obviously base 10.
That's
If
okay.
it's,
That's okay. That's okay. That's okay.
it's fine.
Actually, see, both way it is fine, but it has to be mentioned that
Yeah.
logarithm we will have to take.
Yeah.
Uh,
So it does not affect the value of uh, the maximum value until and unless it depend on the log. So the estimator is actually depend on the log. So now
hmm.
it affect the value, right? So we are getting n over summation of log xi.
Hmm.
So that is the case. But some of my friend use ln. So
That's okay. That's okay. We'll take care of that. Okay.
okay, thank you, sir. And there is one more question, sir.
Uh,
EM, should I ask that?
yeah. Tell me.
Yeah. So EM in EM algorithm, sir, we have two steps, E and M. So E is just used to calculate the parameters, right, sir? Like mu
Sorry.
and what do you say? The in E step, E is used to calculate the parameters. Like three parameters are there, na, sir? Mu and sigma and lambda.
Huh?
So what is E used for? Like E used for these three parameters or for maximizing the data or
No,
whatever the question.
which?
Generally,
No, no, no. Can you just repeat it again? For which question and what are you talking about?
actually, yesterday we got one question. There is some. It's just a small application key. Some information. I didn't remember the question completely.
It's okay,
Eh,
but related to which topic?
so it's related to EM algorithm. So they are just actually asking
Okay, okay.
what is
Expectation. Okay.
yeah, what E represent and E and why like for what purpose we have to use E and for what
Expectation
purpose we have
step
to use
and
M.
yeah, I remember. Yeah, expectation step and the minimization step, right? So
Yeah, maximization. Yeah.
yeah. So sorry.
So I'm asking ki M is used for maximizing likelihood, right?
Yeah, but both actually. See, first step is for you will fix lambda, and you will fix theta, right, all the parameters, and find lambda. Okay, that is your expectation step. And in the later case, in the maximization step, what you do, use that lambda and try to maximize the log likelihood of parameters. If you remember that part, okay, I'll show you that to you. Okay. It is week 3, right? Or 4.
So,
I think this was the case, right? Okay.
so expectation is used to find lambda, right, sir?
Yes. So here you can think of, if you think of this, are you able to see my screen?
Yes, sir.
So you see that here what you do. So you are actually keeping this all parameters. Theta means like all parameters, right? All like pi, then your mu and sigma, right? All these parameters, you keep them as constants, or sorry, you treat them as constant and try to find out lambda, right? Which is I think it is called as a latent variable, correct? And then by using that, in the next step you use that lambda which is used in the like found out in the previous step, treat it as a constant and maximize for theta. So this is maximization step and this is expectation step. Got it? Is that okay?
Yes, sir.
So basically, here all of this theta, you start with this theta, and in one of the steps, right? So expectation step, what you do is you treat theta, like all parameter which was there, like let's say initialized, right? So all this theta zero, we treat them all as constant, mu naught one, mu naught k, and all, and you, so this log likelihood, right? Which is, I think this one, this part, right? This part you treat this aik as constant, and you uh, maximize for, or you differentiate with respect to this lambda, correct, right? And
Yeah.
that will be your t plus 1 step, and whatever you got in t plus 1, so let's say it's, if you start with theta 0, this will be lambda 1. You treat that lambda 1 in the next step as constant, and then uh, like then differentiate with respect to all theta 0. So in that case, this theta 0 will be uh, like we differentiate with respect to them. So all, like let's say it will be a partial differentiation, right? First you will do it for mu, then do it for sigma, and then do it for pi. It likes again. So when you are doing for mu, then sigma 1 and pi 1 also treated as constant. When you do it for sigma 1, this 2 will be constant, like that. That is a step. That is called expectation maximization. Right? So this is expectation step, this is maximization step. Okay?
So we can say, sir, E is used for
This is step.
computing expected
Yeah.
values.
Huh? Computing?
Expect, sir, that was actually theoretical question.
Correct.
This
I know.
numerical I
I
got it.
know. Yeah, I
Yeah.
know. So expect, why it is called expectation step is actually I think there is
So that was related to, like, there are two options. One, like something expected values of latent variable.
this
Another
is
is
a
to
variable.
maximize the update the parameter, or you can say to maximize the expected likelihood.
Correct. So see why
So
why this is called expectation step. If you see this expression of lambda, so why it is latent variable, that
the word expected is not given in the question. It is given simply like
that is okay.
compute the latent variables,
Correct. So
number
what?
of latent variables.
Yeah. What is,
Yeah.
what do you mean by latent variable?
Actually, I don't know, sir. The word latent is in the
Is there? Is
question.
there in the lecture? It is there. Sir has used
Yeah,
latent.
latent variable means the variables which we are calculating,
No.
sigma,
So
mu,
you
isn't
can
it?
think of it as like that. The latent variables are the variables which are actually not the part of the distribution. They are introduced out from like outside, or like they are generated. So for example, if you think of the clustering
Lambda.
problem, right? Yeah. So in the clustering problem, the k-means clustering, the zi, right? That is indicator variable. That is not
Yeah.
right. We are introducing that there. Zi.
Oh, okay. So,
That
so
is the
these are
latent
the
there.
latent variables.
Yeah.
Like
So
in this, in EM, we introduce
lambda.
lambda, sir.
Right,
Yeah.
because lambda was not there, right, initially. For
Yeah, yeah. So we
for
introduce for the
simplifying, yeah,
for using the
yeah,
theorem. Yeah.
correct. So by that Jensen's inequality, we wanted that lambda. We introduced that lambda, that extra variable we have introduced. So I think
Okay.
somewhere sir has mentioned about all these latent variables. But yeah, I think see, it's like I think it is coming for one time, so it is possible that you might have forgotten. But yeah, that is why that lambda is called as a latent variable. And why it is a,
Latent variable, I think we did not heard in the lectures.
no, it is there, it is
Anyway.
there, it is there, it is
It
there.
is there in the lecture, but sir, didn't take it seriously.
Yeah, that see, that is what, right? So
He
this is,
maybe actually we just assume the teacher said that we take one extra parameter lambda from our side. Don't worry, what is it? That's how the sir
no,
explained.
but
I
see,
will explain at the end. Yeah, he just introduced
if you wanted to
like
learn about more in machine learning scenario, right? So these latent variables are very important. So see, currently that MLT, whatever the syllabus is, right? I will say that it is not like all the things are there, because if you try to cover up all things, right, this will not complete in 12 weeks. It's like a very vast thing, right? If you go mathematically, we don't need that much. Again, I wanted to tell you that why it is called maximization step, right? So if you see this expression for lambda, this is looking like, see this probability of zi equals to k, there is pi k into some probability, right, and divided by probability of xi. If you think of this as like probabilistically, it will be looking like as a some expected value, right? How do you find out the expected value for any, let's say if you have some random variable x, which is a discrete random variable, how will you find out its,
Yeah, it's similar to the logic like number of heads divided by
yeah,
total number.
yeah, like that,
Head and
right?
total.
And that is kind of a mean, right? Basically you're finding out the expected value of this. If you think of this, there is one, you are just multiplying with some probability, right, to that random variable x. Suppose this is x random variable, multiplying and dividing.
Actually, sir, yeah, in the question it doesn't mention key we have e is ideally e is used for finding the expectation of the latent variable or the variable which we introduced, like lambda in this case, right, sir? E is used for
Correct,
finding the,
correct.
but the word expected is not given in the question. It just simply mean in the question it is simply right
But
key
see,
each
what,
step is used for number of latent
got it,
variable.
got it.
So
But if
that
you,
was confusion. Yeah.
it was clear to you from EM algorithm. What is EM algorithm? Is expectation maximization, right?
Yeah,
Right.
expectation of is for expectation of latent variable.
Ah.
So the word expectation is not given in the question. That's what I'm saying.
Oh, okay, okay.
Yeah. So and just it's simply given key each step is used for number of latent variable or each step used for latent variable, something like that. I'm not sure.
Ah.
So the word expected is not given in the question.
Okay.
In the question, yeah.
And that
And
is,
for lambda, for m step, it is given like key to maximize the variable, something like that.
ah,
So,
maximize the likelihood of the variables.
yeah, maximize the likelihood. So
Correct.
that's, I think that's what I put in the exam. But
Let
I
us,
was
let us,
confused because the word expectation is not given. That's why I'm yeah.
yeah. So that's, so that is why we, whenever we try to formulate like questions, right, it is like we try to see, at least you got to know, right? Now
Yeah,
you
but yeah, I got to know. But this is the correct like each step is automatically mean expectation. So that the word expectation should be mentioned. Uh,
I think it
in
was
my opinion,
what was
maybe
what was there written when you say that E and M. So E step, do you need that step to uh, get the latent variables or get the expectation for the latent variables? So if you have that, only two options were there, I guess.
yeah, in that sense, yeah, yeah.
So if you think
I got
of, I need to find out. I think it was like you use that E step to find out the number of latent variables. Is that correct? No, right? So like if you discard one option, definitely the second option will be correct, right? I think there were four options. One is for
yeah.
each step, like two are for each step and two for M step. So if you think of one of the, I think one of the options, it was saying that E is used for finding out the number of latent variables. If it is finding out number of latent variables, at the same, like once I read it, at that, like at that instant I should scratch that option, right? Definitely it is not going to find out number of latent variables, right? So
Okay, and so what about the other option? Second
okay,
option,
I don't have, I don't remember all. So once I'll see that questions, right, then I'll maybe at the end of this session, maybe I can see that and I'll let you know.
okay, sir. Okay.
When the key
Thank
will
you, sir.
come? When the answer key will come?
I think it
It's
will
not
come in one or 2 days.
Hello.
Yeah,
Answer key will come when?
1 or 2 days, 1 or 2 days, possible.
Okay. One
So this
question about
time
the
the
also.
paper is tricky. Wait.
Huh?
This time the paper is good. Actually, they just want that we have to use our minds in a good way.
Yeah.
Yeah.
So
From the last PYQs, this time
I
the
think
paper is
I think we
yeah.
didn't. I think before the session also I told you that the question paper should not be much numerical, right? It was like theoretical. If you think of that, right?
Yeah.
Some of the questions.
Just only one simple question to pass the students, given just like finding covariance matrix. That was a very easy question.
Yeah.
Only.
But whatever we did now, according to the PYQs, this was a very good thing because it will be very useful. If you forget about the quiz one exam, na, we did it a lot of things in the calculation also, and how to do the k-means like that. That is a very good thing.
Quiz to paper will be also like that. It will be like mostly it is like understanding of yours, like mostly
Yeah, that
regarding.
was a very good practice we did before the exam.
Yeah.
The PYQs. It is the best session we did it.
Okay.
The collection of the week-wise collection was very good. That was very much required.
Yeah.
We did not get at the time of examination. We have to go here and there. One question was that where the k mean the number the k was limited to limit the k. This was correct, na? For k means k plus plus. K
K,
means plus.
What was the question? Can you tell me? Like, I don't remember all the questions. So,
So
radical like
in
if we
yeah,
use K plus plus in place of K, something like that.
yeah, the simple thing is that whether in which method k is limited.
K
We
is
fix
limited.
k. Yeah, we fix. Our motto is to limit the k clusters, number of clusters. Is it k means plus plus?
No, no, no.
Where we want
No, no, no. I think that not.
in which method? In which method we
Check.
limit the number of k's?
So
What
it's
Number of
case
starting question only.
Okay,
I didn't remember that question also.
let
K
me see.
is not a part of this algorithm. K is to be as a weird specific.
Used for initialization.
Okay, let
my
me.
question.
So which question you are referring to?
No, one question was there where the option was there. The theoretical type of questions were there.
Yeah, but
Multiple
what was the wording?
wording I can't remember, but the main thing was that
K
in that
means or
in the
K
in
plus plus related.
yeah k plus plus means k means plus plus in which in which our mission our motto is to
Yeah, okay.
limit
So the
k.
question was like this, no? How does K means plus plus algorithm?
Number of iterations. Maybe the question is on number of iterations.
Okay,
Number of iterations for convergence could have been the question.
I'll tell you.
Yeah, perhaps
Sir got the question. I think sir got the
Because the
question. Yes, sir.
reason why I'm saying this is K is decided beyond the system. We specify.
yeah
So the system does not choose K.
yeah
Okay, I'll tell you the exact question. The question was, how does K means plus plus algorithm enhance the initialization process
Initialize.
as compared to the standard K means algorithm? I think that was the question.
Yes,
Yes,
that I
sir.
remember. That I remember similarly.
And that option A was it ensures the algorithm, or okay, one of the options was it ensures the algorithm converges in a fixed number of iterations.
yeah. This was correct or wrong?
No, wrong. That is wrong.
Oh, that is
Because it is initialization process, right? So the second one is it improves centroid initialization by spreading them out and leading to
Yeah, this is I think
okay
correct.
Yes, sir.
is the
okay
correct one.
Yes.
Because
okay.
in K means plus plus, yeah, you
No,
do just a minute. Let me finish. So when you in K means plus plus, what it does is you try to find out the probabilities, right? You select first cluster randomly, first centroid randomly, and you find out the distances from that cluster, like for all the points. Then what you
Yeah
do is you divide that by total distance, and like you just probably you just converted them into the probabilities, and you
yeah
choose and you choose that centroid which is as away from, or okay, in that case you choose that centroid, the second centroid whose probability is higher, right?
yes
And when I say the probability is higher means what, you are actually choosing the like largest distance, right, from that centroid, because then only that ratio, the distance divided by the total distance, will be higher, correct?
yes
So that means you are ensuring by using K means plus plus is that the centroid for the second cluster, let's say if you have first one, first cluster centroid, you are choosing the second centroid such that it is as away from the
yeah
first
away
one.
first one.
So
So I have a doubt regarding this.
yeah,
So isn't the very mean of K means plus plus is that you keep the data points far apart, where each data point is considered as a centroid of its own.
see what actually is, no, it's not like centroid like that. Let's say you have 10 data points, suppose, okay, they are like scattered everywhere, is that fine? Now
Yes, sir.
you choose one, anyone, randomly, okay, I picked one, and what I'm doing is I'm just finding out, but I need to find out the second centroid, right, for
Yes, sir, which is the farthest away from this one.
yeah. So what you do is from this point you do what, you calculate the
The distance.
distances, Euclidean distances for all remaining 9 points. Correct?
Yes,
Now
sir.
you choose that point as a centroid, which is like farthest from the first one. So it also ensures that the nearest ones, right, for the first one, they actually fall into the first uh, centroid. Like let's say 4 or 5, let's say they are like nearer to the first one. One of it will not, like, we are not going to choose that, right?
Oh,
Okay.
yes, sir. Got
You
it.
understand?
That
Okay.
the
So
only the farthest away will be chosen. Yes, sir.
correct. So I'll maybe I'll just share my screen and try to.
Thank you, sir.
Yes, sir. Yeah, this is the fundamental thing. Correct. You are
So
right.
let's say, I think, see, this is the case, right? So okay, I don't know what is. So now let's say these are the data points, right? 1, 2, 3, 4, 5, and suppose 6 is there, 7, 8, 10, right? Now
Yeah.
suppose I have chosen this as centroid. Okay, so in k means what happens is, it is possible that it will choose, because we are choosing randomly, right? It might choose this point as a second centroid, fine, because it is random. So randomly you can do, like, every in case of random initialization, what happens is every data point will have the same probability, right, to be qualified as a centroid. Is that correct? If I say k
Yeah.
equals to 2, if I say k
Yeah.
equals to 2, so it is possible that this and this can be considered as the initial centroids, right? And then you do the process, iterative process, and then it end up might be choosing this and this, right? But in k-means plus, what you do is, initialization we need to improve, right? So you chose first randomly. Now what you do is you calculate the distances, and so and then what you do is you choose that point as a centroid, which is having the higher probability. What does that mean in second sense is that will have the centroid should be as far as from this. So definitely these points will not qualify, right? In that case, right?
Mm.
So that way you are already choosing the kind of correct clusters, right? Now you don't, if you again run the algorithm again, it might end up being this centroid and this centroid, and that way uh, the process will become you know kind of, so initial, because your centroids will again basically depends on what, how your initialization is done, right? It is done wrongly, then the cluster centroids might be at the end of the convergence, because k means doesn't guarantee you the optimal convergence, right? K means doesn't guarantee you the
Yeah.
optimal convergence. It
Yeah.
will
That is local. That is local.
local. So that means you might not
And which one gives the optimal?
uh, basically this, it's like controversial to say that okay, this will give me optimal, but I think,
Okay.
see, EM
EM,
is better.
EM.
Yeah, EM is better.
Isn't it a
Okay.
NP hard problem?
Yeah, that is what. But still EM does it better, because again k means, so with this initialization also, right, k means plus plus, that also might be giving you the good clusters. Why EM is better is, I'll say that because in AM algorithm what you do is, whatever the cluster centroids you have obtained from k means, right, you actually use them as the initialization step in the
Yeah.
initialization,
Yeah. Yeah. Yeah.
right? So now you are actually again looking into more probabilistic way, once you're done, or once you're end up doing like running that k-means algorithm. So that way EM will do better, correct, right? I think
Yeah.
if you remember that part also, this
Mhm.
EM algorithm, so, yes, fourth one, right? I think somewhere it is mentioned that okay, I think, okay, latent variable also, okay. This is called as latent variable, right? Unobserved or latent. So this cluster indicator is also latent. Similarly, that lambda also is a latent variable. Okay, I think it there in this case. Here, right? Okay, see, it is written, right? Usually comes from the Lloyd's algorithm. So Lloyd's is k means.
Mhm. Yeah.
So
Yeah.
here initialization will be that one. which is already we found out by using Lloyd's algorithm. So whatever best solution you have found out from Lloyd's, you're actually taking it as this initialization step for EM algorithm, and now you are again doing it, trying it to do better on this, right? So possibly EM does better than the k-means. Okay.
Yeah, go back once again. EM,
Okay.
just
So,
that's that.
so can it be said that first we find the k means the value of k we are taking, then
Yeah.
we are refining it with EM.
Yes, you can say that.
Yeah,
One of the
yeah,
ways. See, it is not like hard and fast that you should do
yeah,
it. It can be random also, but generally people do this because that way the time for processing EM algorithm also reduces, right?
Yes, sir.
Because you don't need to iterate much again.
EM convert. Go below. Yeah, just
This is algorithm.
converges. Yeah. No, converges the local.
This also, can you see no no algorithm actually guarantees you that it will give you the optimal clusters, right? Like, but
Okay.
we are not worried about like optimal clusters. We are like,
The question was also there regarding them. Question was there
question
for the optimal.
I don't think it was there.
One
uh,
question was there.
okay, let us see, like once the question paper comes out, right?
Okay. Let us see.
Anyway, I have my question paper, but uh, let's
We'll discuss on the question directly so that it will become clear. The concept, at least concept will be clear.
yeah. Okay. Any other? If it is not, shall we start then for this?
Yeah.
Have you watched the lectures? Week 6.
Watch the lecture, but I think very confusing type of
So
thing.
I did the lectures also.
Huh? Okay. Okay. Fine. I understand the concepts are little bit,
Yeah, typical type of thing is that. Yeah,
let us. Okay. I'll try to give you the insights. What does it?
yeah.
Because
So
mostly it
that
is insightful only. Uh,
Mhm.
let us see what we can do today. So I'll try to replicate what sir has done, but I'll tell you that what is the importance of it, right? If in case you don't understand it watching the lectures, because it will take like multiple rounds of watching it, understanding it, going through some books and all. So let us see how much we can discuss over it. um, okay. So we have seen linear regression, right? Weak 5 linear regression we have seen, and with the sum of squared error loss, or if you think of it like, okay, first of all, what is the solution for sum of squared error loss? That is equal to W at ML. Have you seen that?
yeah. In week 5.
So when this will happen? When we solve this problem, right? Y minus, I think, W transpose X square, or you try to arg min, right? So let's say you try to minimize this quantity, right? Basically.
W transpose X minus 1.
Huh? Yeah, same thing, right? Anyway, it's square, so it doesn't matter, right?
Yeah.
uh,
Yeah.
so if it is square, then, and if I'm saying that length of square, that means each of the quantity is
Same.
getting squared. So either you say W transpose X minus Y, or Y minus W transpose X. After squaring, you will get the same quantity. So you try to solve this problem. That means try to minimize the squared error loss between the true label and the predicted label. And
Actually, it is a error, only.
this is the error, right?
Yeah.
Between the true labels and the predicted labels.
Yeah. Correct.
Okay. And we have found out the solution for this. And what was that solution? Solution was XX transpose. Uh,
Pseudo inverse.
yeah. So pseudo inverse we use in, let's say, okay, here also we can use, right? Okay, fine. I think
Pseudo
yeah,
inverse.
pseudo inverse and inverse is fine.
We do not understand the pseudo inverse also in the last class. It was pending.
Pseudo inverse
Why?
is basically, you see
What?
that if your matrix is not singular. So I told you, right? When you call the matrix as singular, what is the what is how
Determinant equal to 0.
Determinant is
It,
0.
if determinant is 0.
what you can say about, let's say, if any matrix is having determinant as 0, does it can you say that it is a full rank matrix or not?
No, it is not a full rank matrix because
Matrix. Because the determinant is 0, it is not a full rank matrix.
right? No.
yeah,
And if you another way of looking at it is like one of the eigenvalues of it should be equal to
0.
0, right? Is that
Yeah,
correct? So these three are the main things about when you say that a matrix is singular. But another part of it is when you calculate inverse, right? So any matrix is called as a invertible matrix when it does not have a
When the determinant is not 0.
not equal to 0, right? Why it is that? Because I think, let's say if A is a matrix, its inverse can be find it out by using, I think this, right?
yeah.
Determinant of A
Determinant of A into
and
the
Add, add, add,
cofactors.
add, yeah,
Cofactors of A.
adjugate of that.
yeah,
Yes,
so
adjugate matrix of A, which is the combination of the cofactors.
cofactors, right? So
Yeah,
is that correct? So if your
yeah,
determinant is equal to 0, what will happen? This quantity will become infinite, right? Because
yeah,
so that is not possible, and hence for singular matrices, finding out the determinant is not possible. Okay. Now
yeah,
this X6 transpose is one of the matrix. Suppose this is also one matrix, right? X6 transpose. uh,
yeah.
and and we don't know whether it, like, okay, for some data points it is possible that X6 transpose is not a singular matrix, but suppose if there is a singular matrix, that means we will not get the solution W star, right? Correct. So what does that mean is, if the matrix is not invertible, anyway we are not going to get the solution. But then it will be, again, see, that's the problem, right? Again, if I don't be able to find it out, then it's not good. So there is one method in linear algebra which is called as a pseudo inverse. So what you do is, instead of finding, so you may consider that. So how does it will look, that matrix? Possible way of explanation is this, right? Or like after row echelon form, I think we should get that all zeros at the end, right? Because it's not a full rank matrix, at least for one
Yeah,
row.
yeah, at least for
So,
one.
so for, if you can actually be able to find it out without considering that row, you can find out the pseudo inverse, or you can find out the inverse, right? Then that inverse is not the true inverse, but it is called as pseudo inverse, right? Because we need to find out the inverse somehow so that I can get the solution. Okay, again, for that you can actually refer to there is one good lecture on this, right? Like how to find out pseudo inverse by Gilbert Stein. You can
Where it
refer
is?
to that.
Yeah, where it is?
Gilbert Stein. Gilbert
Okay.
Stein is actually is a good professor. Is now, I
Yeah,
think,
yeah,
retired.
yeah. MIT, no?
Yes, yes. So
I have
he,
seen, but how
yeah,
to find the pseudo inverse where it is?
I think it is there. I think there is one of the lectures. It is there in that
Okay,
playlist of linear algebra. There is somewhere it is, or you can find, like, so many resources are there. But I think this one is better because
okay.
he actually teaches.
You meant to say the pseudo inverse we can calculate by the reducing the row echelon from such a way that the
No,
last row is
it
usable.
is layman terms. See, I'm not telling you the exact
Okay,
there. I'm
okay. So
just saying
what is the method to get the pseudo inverse?
you can find it out. See, if I start discussing here,
Okay,
again it will
okay,
take time.
okay,
For now,
okay,
it is not important how to find it out.
okay,
Anyway, it's like out of scope for this syllabus also, because we are not
okay.
asking you
So
to solve.
basically, we are just asked to find the normal inverse. That is a symmetric matrix is usually given.
Yeah, correct. So generally, the question paper also, we don't ask you to find out like pseudo inverse and all, because it's not in the scope of
Okay.
this syllabus. So
So
we,
we can treat it as an inverse for the time being, right?
yeah. Okay, so
Okay.
that is what. So it's okay. So the thing is, this is your W star solution, right? And we found out that if I try to see it through probabilistic view of it, we said that if given X, how the labels are generated, we say that it is like this, right? W transpose X plus epsilon, correct? And what is epsilon? It is a noise, and noise, we are assuming that it is Gaussian noise, right? Okay, so we are saying that each of this label can be replicated by adding the Gaussian noise. And if I do that, the solution which we have found out by using the squared error method is same as that the solution we have found out by using the W hat ML. Okay, why we are using okay, W hat ML? because this is probabilistic view, right? We are actually now getting some distribution to it. And what kind of distribution it will have for this? It is normal with mean. Can you tell me what will be the mean?
Mu k.
No. By looking at this expression, can you tell me what? So this is 0 sigma square. Okay, I'll tell you one more. Maybe. Okay, have you seen the Gaussian curve? This Gaussian, correct?
Yeah.
So this 0 is the mu and sigma square. So if I add, or okay, maybe I'll just tell you like this: y equals to, suppose, should I say now? Suppose some constant plus say epsilon. Okay, this, or let's say x. Okay, and let's say x is normally distributed with 0 mean and sigma square as the uh, variance. So what will be the distribution? And let's say y is equals to c plus x, and c is some constant. What is the distribution of y? So it will get
So
shifted,
the
right?
mean would become C.
Yeah. So how we have found out it? Like, let's say expectation of y is equal to expectation of c
C
plus
plus X. Expectation of
expectation
X.
of x, right? And what is the expectation of x? 0 plus expectation of c. Expectation of any constant is constant itself, right?
Constant.
So that means expectation of y is c, right?
Okay.
And what will be the variance of y? So variance of y
Why?
will be
So why the expectation of
variance of c plus variance of x, right? And variance of any constant is
0.
0, right?
0,
Because
sir.
there is
Yes,
no
sir.
variability. And what is the variance of x?
We have taken it to be sigma square.
Here we have taken it as sigma square, right?
Sigma square.
So variance of y will be
Sigma square.
sigma square. So the distribution of y is normal c comma sigma square, right?
Okay. Yes.
Correct. And now I say now, like, this is the variable y given x is the variable. I'm just saying that it is equal to w transpose x plus epsilon, and here epsilon is distributed as normal 0
With 0 mu.
0 sigma square, right? Okay, so in that case, what will be the expectation of y given x? So that is expectation of w transpose x plus expectation of epsilon,
Yeah.
right? Okay, epsilon, fine. Okay, what is the expectation of epsilon?
So for epsilon, it is 0.
0. And what is the
And for
expectation
W
of,
transpose X, it is a constant.
It will
so
be W transpose X.
right? I
This
hope
is
you
a constant. This is constant, not W transpose X.
yeah, that has to be constant, right? Because it is
Yeah.
a dot product between two vectors, right?
Yeah. Dot product of vectors.
Between
Yes.
w and x. So even
Sir,
though
can you please explain the expectation of the epsilon is y0?
it is given to me, right? What is
Okay.
epsilon is actually distributed according to this, right? We have assumed that this epsilon is what? Noise, right? Noise in the labels. And we are
Yes, sir.
saying that this noise is Gaussian distributed, right?
Yes,
so
Correct?
yes.
why the
Okay,
expectation of x is 0?
So we can say that because it is random, the total sum cancels out each other.
which one? Which sum?
So why the mean is 0? Can we probably say that because it is in random directions, the total sum cancels out each other.
About why you are taking the? I'm sorry. Can you just okay? I don't understand it. Like, if you can explain
So
it really to
why
me.
the
Ah,
expectation of the error is 0? Why can't
okay.
we take any other value?
Okay, so what we are, yeah, so one of the reasons is we are actually using the squared error loss, right? Again, it is our assumption that whatever the errors are there, what are the errors here? These are the errors, right? Correct, right? So this is your true label, is that correct? The actual label, this this is the proxy, and what is the proxy here? It is W transpose X, right? Is that fine or no?
Yeah, it is.
Yes, sir.
Or okay, I can say that this is, let's say, actual X1. So my proxy is W transpose X1. Is that
Transpose
correct?
X1.
Now,
Yes,
and
sir.
there is some error here. Now this error plus this, I'll say that it is should be equal to X1, basically, right? Or in this case, let's say Y, because that is our label corresponding to it. But that is what our assumptions is. Again, we are saying that this data is actually yeah. So you can, one of the way of saying it as, it will some of the data points are above the line, right, and some of the data points are below the line.
Below the line.
And in general, in our real life scenarios, we know that most of the problems, right, or most of the things, they are distributed according to normal distribution, right? Suppose the you say that the height of the people, right, of the entire population, we assume it as a normal distributed, uh, and you can actually show it by using the central limit theorem also, right? If you just add all
Yes,
of
sir. Everything can be reduced to a Gaussian distribution.
uh, so general purpose, your our all if you think of, and this noise actually is what, this is the sum of all, right? Like epsilon 1 plus epsilon 2 plus epsilon 3, like that, right? It is sum of noise, right? The total noise. So might be it, like each of that it might have some different distribution, right? Each of the, but if you take the sum, an entire sum, I can actually show by using the central limit theorem for
Limit
large
theorem.
number of n. For large number of n, it might be going around that normal distribution, right? Again, the assumption is that we are saying that this noise is centrally distributed. Why is that possible? Because some of the errors, right, let's say this is plus one e1, this is minus e2, right, this plus e3, and this minus e4, like that. So we are saying that if I add all of them and try to get out the mean, it might end up into zero. That is our assumption, basically. So all of this is assumptions, right? So if you don't think that this noise is normally distributed, there is another example I think sir showed, right? You can think of it as Laplace noise, and then accordingly your solution will be changed. Correct? Right?
Yes,
Okay.
sir.
Yeah. So till now, I think if all of you are here with me, then we can actually understand it as like this. Uh,
Expectations.
so we were saying that y given x is now normally distributed with what is the expectation here? W transpose x.
Yes,
W
sir.
transpose X sigma square.
The expectation is W transpose and variance is sigma square.
Yeah. Okay. Sorry. Plus should be right. Sigma square. And with this, what was our ML hat? That also has actually was like this, right? W, oh sorry, it is equal to W star, and which is nothing but X transpose pseudo inverse or inverse XY. Is that correct?
Yes.
Yes, sir.
Okay. Now, I'm just going to talk about something different here. Uh, Maybe I hope all of you have actually gone through the stats courses and all. You might know the bias. What is, like when you say biasness and everything, right? I hope all you understand
Yes.
that biasness, right? So,
Yes.
so our data set is actually how does it looking like? How is that data set? X1, Y1. Here it is x2, y2, x3, y3, and up to xn, y, right? Is that correct? And each of this y1 and yi, I can say that it is equal to w transpose xi plus epsilon I, right? Is that okay? Okay.
Epsilon I is for
Each of
individual.
yeah, individual it will be different, na? Error will be different, right?
individual xi or xi?
No, individual there. So why it is individual? You just see, like if you have
Okay,
data
fine.
points,
Yeah,
the
yeah.
x1 will have its corresponding error, right? X2 will
Hmm.
have its corresponding error, like that,
Okay, okay, got it, got it.
and accordingly you will get that y1, y2. Fine.
Hmm, hmm.
Uh, but this solution which you have got, like x6 transpose pseudo inverse xy or x6 transpose inverse xy, uh, is it a true W of? Uh, I hope you understand the concept of sample and population.
Yeah,
Right? Sample and
Yes,
population.
sir.
So population is like the entire data set which you are having,
Entire
right?
data set.
Entire data.
yeah, yeah.
And sample is like few of the
Subset,
Representative of the population.
yeah, subset of the,
subset of subset
correct.
of population.
So okay, I'll just try to show you that example. So this is, let's say, population, right? And this is one sample one, I'll say, and there might be another sample we can pick, right? Hmm?
Hmm.
Right. So suppose I'll call it as D1 and I'll call it as D2. What let's say this is D1 data set. So and let's say there is another D2 data set which is again some other samples, right? Is it possible? Right.
Pardon, pardon, pardon.
See,
So it can be because it is randomly we are selecting from that population.
correct, right? So I don't know. Let's say any manufacturing is happening here, right? And you try to get the forecast of sales, for example, right? Based on the quality of the product or something. I'm not sure like about what example. Or let us say, okay, simple example. You know that house prediction problem, right? You
Yeah,
have different,
house
Yes,
price.
sir.
correct. You have different features,
Square feet. Yeah, yeah, yeah.
right? So let's say xi will be in how many dimensions? It will be in d dimensions, right? D features
Yeah,
you will have,
yeah.
and uh, and yi will be in r, and if xi is in rd, then w also is in rd, right?
RD.
Correct. I hope all of you remember that. Now let us say you have taken some thousand houses price, like all the features, right? For thousand in one locality. Let's say it in Chennai, or let's say Pune, or let's say Mumbai. Any place you choose, you have taken thousand houses. That means what? Have you taken all the data set in that city, or have you taken only sample of it?
Sample.
Right.
Sample.
So you have
It's a
chosen,
very small sample.
yeah, let's say it's okay, very small and all, it's fine, but it is like, let's say you are taking it randomly, right? And based on that, what do you think that w hat ml for data set d1, and you have chosen another thousand randomly, it might it is possible that some of the houses in data set 1 and the data set 2 are same, right? Because we are choosing it randomly. Now you
Yeah,
have collected data for 1,000 houses randomly, let's say in a Chennai city, and let's say, and I have also chosen some 1,000 houses. Like I have data set of 1,000. That is, let's say, different from whatever you have taken. Does this W hat ML will be same for you and me?
Yes, sir.
Will that be same or will that be different? By looking at
It
this
will be same.
example, no, you just think about
So
it.
from here, from the equation, it seems that they are the same.
Why? My x's
So
are
bias variance trade-off.
no, that bias variance, we haven't talked about that yet. But what do you think that?
it will be different now because both are
Correct.
only some data is only common. Other data are different.
But see, now the thing is, what we are saying is that w hat ml is what, a random variable, right? So w hat ml actually, see, w hat ml is the solution. So that anyway is going to be correct like for you and me, it should be same. But the thing
W hat
is,
ML. W hat ML is the maximum likelihood. Na?
correct. So we are maximizing the likelihood, and at the end of it, it should give me the final answer, like straight correct answer. But you just think about it. Every time it might be so that w is, since it's a function of what, or w hat ml is the w hat is like the final solution, but I don't
function of the data and the level.
right. So here my label is a random variable, right?
Yeah.
Why is the random variable again, right? Because, and that's why we are actually saying that why it is
Yes.
only random variable, because given the x we are actually trying to find out its distribution of y, right, label. And in this case it's a random variable. Now you're, when you just collect it like that, and if you use different samples, right, you will get like different w's, right? And now you're actually finding out that solution which maximizes the likelihood, right? And at the end of it, it should like whatever we have collected all the data samples, it should get the same what do you say, same answer, right, for w at ml at the end. Now one of the important properties of it is it is to be known as that, okay, okay, that w at ml is what, is an unbiased estimator of w. But is w at ml is a true w? Actually it shouldn't be, right? Theoretically it shouldn't be, right? But we know that it is a unbiased estimator. Biased estimator of w, right? So when I say unbiased estimator of w, what does that mean? Expectation, right? Expectation of, we are considering w at ml as a random variable, and if I find out its distribution, the expectation of w at ml should be equal to true w, right?
Yes, sir.
That is the meaning of unbiased ness, or in another word, like let's say bias is defined as what? Bias is equals to expectation of the random variable minus the, or like whatever the
Actual value.
actual value of the parameter. But do I have idea about this w, actual variable? No.
No, sir.
No.
So we are just, that's why we don't have the actual understanding of this w. That's why we are finding out different methods to find out the estimation for that parameter, right? So whatever the expectation of w at ml is there, so this w at ml, if I treat it as a random variable, does it have some distribution? Does it have? It will have, right? For different data set it will be different, right? Suppose this is
Yes,
the
sir.
distribution, and the mean of this w at ml, let's say this is expectation of w at ml, right? So some, these are all w at mls. What we are saying is that the mean of this w at ml, right, that is equal to w, true w. Understand? I hope you understand that what I'm trying to say. So you choose one data set, you find out its w at ml. I choose one data set, I'll find out its w at ml. So let us say there are like thousand of us, right? And we are actually performing that experiment by choosing different samples of these houses, right? And we are finding out our w hat ml, okay? And now all of this thousand w at ml, right, they will actually, so thousand, when I say, it's like just to understanding purpose, it will have some distribution, right? Is that correct? Hmm? And this distribution, let's say it looks like this, but the expectation of this distribution, right, the mean of this distribution is actually equal to the true value of this w, right? In this case, the parameter of from where actually we are getting this data set, or this data set is generated from.
Sir, so this is basically because we are taking it as an unbiased estimator.
Yeah, actually we can show that it is unbiased estimator, but right now just understand that this is an unbiased estimator, okay? If it is
Yes,
not,
sir.
then it will change, right? But just
Yes, sir. Certain constant could be added and all that.
correct. But basically I can show you that it is unbiased, but fine, right now think of this as is an unbiased estimator,
Unbiased. Yes, sir.
okay?
Yes, sir.
Because that way the next is like whatever we are going to discuss, right, that will be easier for you. Now I know this W at ML. There is one more term. If you remember from stats, right? There is this term: risk is equals to bias plus variance, right? If you don't remember, you go to stats 2, and this is what the term is, that bias plus variance.
We remember it in the stat
Yeah,
2, but
yeah,
conceptually we are not understanding why
correct.
it was done.
So let us say risk is actually is this one. Risk is this thing. I think when you watch that lecture, you might have seen this quantity. Expected value of the W hat ml minus W, right? It's square. This called as actually mean squared
No.
error.
Yeah, this is error, no? Error. Expectation of the error.
Expectation of the error,
Yeah.
but
Mean squared error.
that is called expectation of the error is what? Mean, right? Generally we call as mean, right? Hmm?
Hmm.
Correct, right? And this is a squared error. So what is this error here? Is this the error between the true label and the predicted label? No, right?
No, no, no,
It
no.
is the error between the actual uh, actual W, that parameter. This is, we are not talking about now the labels, right, of the linear regression.
Yeah,
We are
yeah.
here we are talking about the error between the parameter,
Yes,
right?
sir. The square is given.
Okay, and that is, this is a squared error between this parameter, right? And if
Yes,
I
sir.
find out its expectation, and
Yeah,
that is
this happens to be when we do this parameter,
Hmm.
the maximum likelihood,
Hmm.
and that we are measuring the maximum likelihood, right? Here,
yeah, yeah, yeah.
right?
So
Now
correct,
we are measuring the maximum likelihood error, right?
maximum likelihood error.
And error of the maximum likelihood. What we have calculated from data, a maximum likelihood, and we are
That,
calculating here the error of calculating the maximum likelihood. Is it? This is the error, right?
okay, so I think your understanding is correct, but
Hmm.
the way you are saying is probably not correct. So it's kind of, yeah. So you are saying that we have found out W hat ML by
Yeah,
maximizing the squared
yeah,
error loss, like
yeah,
that.
yeah,
And now
yeah.
whatever we have found out W hat ML, you are
Am I
finding
right? Am I
correct,
right now?
correct. So it is the error between the W hat ML which you have found out using that
Yeah,
maximizing the log likelihood.
yeah,
And
yeah.
now we are saying that what will be, okay, whatever W hat ML you have found out, is it going to be the actual W? No, right?
No, no, no.
Because it is a estimator to the true W.
Yeah.
That means there should be some error between these two. And if I take the squared errors, right, for all,
Mhm.
and then you find out its expectation, that is called as the mean squared error here. So whatever sir has mentioned mean squared error here is this one, this quantity. Okay.
Okay.
So
Okay.
could you explain again what is W here?
W. W is a true
Yes, sir.
parameter, no? Okay. Okay. So what we are saying that y is equals to what? W transpose x plus c, right? Okay. Let's say we are not discussing c here, that bias term. But this is what we are actually finding. This is what we said, right? So we are saying that whatever the labels are there, they are the linear combinations of uh, the data points, right? Is that correct?
Yes, sir.
Right now, but this W we do not know, right? What is that correct W is, right?
Yes, sir.
So what you do is you just add some epsilon here, the noise here, and you try from the given data point you try to generate this part, and from there you use the maximum likelihood estimate, maximum likelihood method, right, to find out, or maybe to uh, uh, I think minimizing that quantity or maximizing the log likelihood, right? So that MLE you find it out maximum log likelihood, and in that case you found out W hat ML, right? Which is not the actual W, but it is like maybe closer to that, right? That is our estimation for the true W, right? Is that fine?
Yes, sir.
Now, let's say 1,000 people have done this experiment. So I'm just saying that w hat okay, w hat ml1, w hat ml2, like that, w hat ml 1000 with different samples. Fine, correct?
Yeah.
Now each of this will each of this will be same as w? No, right? There will be some error here, right? I will take the square of it. Fine, for 1000, right? So this will be your one vector, right? Is that okay? Are you understanding now this part? This is fine.
Yes, sir.
Now this is called as a squared error for each of this true w. It is a error between the actual w and the w hat ml which you have found out, right? Now what I am saying is find out its expectation. So what will be the expectation of this? You consider all of this.
Now,
You
when
you
when
add all of
sample,
them and divide it
yeah,
by 1000, right? Correct.
yeah,
Basic
the
mean, we are actually
mean,
finding out average only, right?
mean square.
Yeah. So you are actually summing it and by dividing it by 1000. So whatever the quantity you got it, that is actually a mean squared error, right? It's average between like w hat ml1 minus w1 square plus w hat ml2. Why I'm taking square here? That way I'm
Positive, positive, positive.
yes, all should be positive, right? Otherwise I'll get like it is possible that I get 0, right? Then I'll
Yeah,
say that there is no difference. So whatever the w hat ml we have got, the that is going to be the same. It's kind of like that. Now you do it for 1000 and divide it by 1000. But when I say 1000, that is what, like, I'm discretizing it. But if it is having infinite samples you are having, in that case, do we do this discrete method, or do you use some other thing, or do you use some, or
So we can take it as a distribution.
yeah, yes, and that is what, like, distribution, right? You're taking integration and you find out this distribution. So this is what we call as MSC, right? Mean squared error. Is that okay? Now this is fine. Do you understand now this
yes,
quantity what it is written?
yeah, yeah,
It is this entire quantity is this. Fine, right? Expected value of this part. Okay,
yes.
and that should be equal to uh, I'm saying that bias. What will be the bias here? What is generally bias is? Expectation of, okay, I think I've done one
Expectations of the,
mistake here. I think that risk is basically it is bias square. Bias square. So it is expectation of w at ml minus w whole quantity square plus what will be the variance?
expectations of
Okay,
W.
so let us say some variance. Okay, I will not go into detail. Right? Let us say some variance. Okay, you can find it out anyway. It is like, it's not like difficult, right? It is, I think, expectation of w hat ml minus w
Yeah,
whole square or something like that.
whole square, whole square, whole
It's
square.
going to be this quantity only again.
Now that will be expectation of W ml minus W square.
Square, yes,
This is the expectations square. That is expectation of squares, right?
correct, correct.
Correct.
So now let us say this is variance, fine, right?
Yeah.
Okay, I hope until this part is fine.
Now W ml minus W is a random variable, right?
WML minus W. Okay, yeah, that is correct.
Yeah. Now this is the random variable. What we have created this data
W
set,
at
right?
M minus W is a random variable. Now you're finding out expectation. Okay, done.
Okay, okay.
So now we are saying that uh, W at ML is an unbiased estimator. So when I say unbiased, then this quantity will become 0, right? Hmm? So that means the squared error here will be equal to variance, correct? So expectation
Yes,
of
sir.
W hat ML minus W square is equal to the variance, right? And this variance, again, I'm not going to calculate, as sir also has not calculated, but you can calculate if you want. That is going to be this part. sigma square into trace of. Is that okay?
How this formula came? Sigma square.
It is, yeah. So actually, if you find out its variance, right? Variance for that. Okay.
Sir,
So
sir also did not derive it.
yeah, this is not derived it, but I think you can derive it again. See, this is what w y given x is there, right? So you already know what is w at ml. You can take this part, right? W at ml, and you will have to find out its variance, right? Variance of w hat ml minus or w, and you can find it out. So you will have to use this part here, and what will be w? You'll have to find it out, and then, or maybe you can take it as uh, I think it should be what it should be. Variance of this quantity minus that quantity. I think that w will be constant. So basically, you're going to find out only, I think, variance of w at ml, which is this one. And if you solve it right, you will get this quantity. So yeah, there will be some steps you can find it. Like if you wanted to find, you can find it online also how to solve that. But important part here is what? Sigma square into trace of x transpose inverse. Is that okay? Now at least you are able to make the connections what it is going to say. I just wanted to show you that what are the connections there. Is that fine?
Yes, sir.
Right?
So can the XX transpose can be seen as a covariance type of matrix?
Yeah, it is a covariance matrix basically. It's nothing but like, nothing different, right? It's covariance matrix only, and it is covariance matrix inverse, right? And if you remember it, like, okay, I don't wanted to say that. Now we will try to find out. So that means what? There is some variance, right? Variance between the actual ml hat and the true w, right? Okay. So understand. So when I say the w hat ml is unbiased, what does it? What I'm trying to say is, let us say this is a distribution of w hat ml, right?
W hat M.
There is some mean to this, and let us say I'll say that it is expectation of w hat ml, correct? And when I say that it is an unbiased estimator of w, that means the expectation of of this distribution
WMN
is
is
equal
equal
to
to the actual value.
actual w, right?
Actual value. Actual
but,
value.
but there is some variance here, right?
Yes, sir.
Right. So so that means this w hat ml is not a constant. Instead of, it is a random variable with some mean and subvariance, right? So that means you are performing this for like so many times, several times, and that's why you got this distribution. And among that distribution, we are saying that whatever the mean of this distribution is there, it is equal to the true parameter, which is w. Okay. And there is
Yes,
some
sir.
variance to it, and that variance is equal to what? This. Okay. Is that okay? This sigma square true this trace of x transpose inverse. What is this sigma square coming from? The noise variance, right? Is that fine? Why? Because y given
Yes,
x
sir.
was w transpose x, or okay, plus plus equal to w transpose x plus epsilon, and it is normally distributed with 0 and sigma square. So it is having so the w hat ml experience, or this variance, right? It is actually dependent on the noise variance and trace of this, right? Means like basically it is dependent on two quantities. So we cannot change the noise variance, right? Because it is there inherently. We cannot change it. Is that okay?
This is sigma times trace of this, no?
Huh.
Sigma square times trace of this, right?
Correct. Right? Okay, right? I hope this until this part is fine. Now
Yes, sir.
I cannot change this sigma square what about the trace of XX transpose? So again, let us
This
say
is
whatever
some of the
sum
diagonal
eigenvalues,
elements, some
or
of the eigenvalues.
right, sum of the eigenvalues. And suppose because trace of the matrix of any matrix is equal to sum of the eigenvalues. So let
Yeah.
us say lambda 1, lambda 2 up to lambda n are the eigenvalues of X6 transpose. And what are the eigenvalues of one of,
Basically, the reciprocal.
yeah,
Yeah,
right?
inverse. Eigenvalue of the inverse of that is right.
The
Right,
inverse will be equal to the reciprocals.
right. So finally, if okay, now can I call it as MSE here for like understanding purpose, like or simplification? I'll say that it is MSE. But this MSE, don't confuse with the that another MSE, right? Which we talked about previously, which is the true label, the difference between the true label and the actual predicted label, right? I hope that is fine. Now,
Yes.
so can I say that it is a mean squared error of W hat ML, right? And that is equal to now sigma square into uh, trace of, I said no, trace of that.
Trace of X
So it
transpose.
is summation of I equal to 1 to D, because let us say X is in each X I was in RD, right?
Yeah.
Right, and then X6 transpose, what are the dimensions of this matrix, X6 transpose matrix? D cross D.
D cross D.
D cross G.
Okay, now if that is D cross D, that means how many eigenvalues should I get if it is
D.
not pseudo inverse, or like let's say it's not singular
D.
matrix?
D.
I should get D, right?
Yeah, the summation of D, right?
So it is summation
Yes, sir.
will be going from 1 to D of
Lambda I.
1 by
uh,
lambda.
1 by lambda.
Yes, sir.
1 by
is
lambda.
that okay?
Correct. Correct.
Until this part is fine, right? So
Yeah.
that
Yes,
means
sir.
this mean square error of W hat ML is dependent on two quantities now. One is sigma square, which is the noise variance, and another is eigenvalues of let's say that X6 transpose matrix, right? So if I wanted to reduce this mean squared error, or can I say that let's say variance, right? If the variance is lesser, what does it will have? Okay, so this was my another distribution, and this is another distribution with same mean, right? Which one is the better one? The
So the one with the less variance.
right. So if I have the less variance, that means the confidence in my W hat ML, right? Each time I'll do, so each time I'll perform, I am actually hitting the very close to the true W, right?
Original value.
Right. So as my variance go like become lesser, my distribution will become like this, right?
Yes, sir.
So that means I'm just trying to get it like as close as to the true W, correct? Because
Correct.
expectation anyway is not going to change. The only thing, so that means if you take the 1,000 samples randomly, if I take the 1,000 samples randomly and calculate the W hat ML over this, uh, the answer which I got and you got, right? Both the answers will be like actually very close to each other, right? Or very close to the true W, right?
Mhm.
So basically, I need to minimize this variance, right? Or the mean squared error between W hat M. Is that fine?
Yeah.
Clear?
Mhm.
But I cannot change this noise variance. So the only quantity I can change is this part, or maybe change, or what do you say? Uh, Maybe I can do some experimentation with is this part only, right? So, but
Which part? Which part?
this part, right? The second one.
Okay. Okay. Lambda part. Yeah.
Right, but again all of these lambdas depend on they are actually this, right? They are the eigenvalues of this matrix.
X6
so,
transpose.
so if I have
Inverse.
x fixed, right, if I have x fixed, I'm not going to like do anything about it, right? Correct.
Mhm.
Okay, but let us say hypothetically, if I wanted to change, how will I change? Should I, if I wanted to add some quantity, where should I put it? And if it is like positive quantity, so should I put it in the denominator or should I put it in the numerator? numerator. Oh, okay. When I say numerator, in the sense in this.
Sir, this is with regarding to MSc.
Yes.
Then we have to put it in the denominator to reduce
You're
it.
right. Here, if I put some lambda or some any other constant which is positive, lambda is, let's say, real quantity, real number, or positive real number rather. Let us say, right? If I put it here, what will happen then? This will reduce, right?
Reduce. This
This
will
will decrease,
reduce.
and eventually the product will reduce, and this. So what is happening now? My variance is going lesser, right?
Okay. Now,
So I think it will increase.
this one.
Huh?
Sir, this will
MSc will decrease, na?
Yeah.
Sorry. I'm not able to hear you properly. What are you trying to say?
MSc will decrease, na?
Yes.
Yeah, MSc is decreased,
Yeah.
but basically MSc is what? It is a variance,
noise
right?
variance into that data variances.
Yeah.
Also, I told you when I treat as W at ML as the unbiased variance,
It will be the variance here.
this MSc is actually the variance, right?
Yeah, yeah.
Right?
Expectation of the error. Yes, it is a variance.
Okay. Till this part is fine.
Yes, sir.
Okay. But okay, so that means I need to somehow do this part, right? I need to somehow add that lambda here, right? Correct. So now let us say, and let us find out, like, let us think about another estimator. Let us say, okay, what am I using the same notations which sir has used, so not to confuse you. So W hat new is, let's say, is this. XY. Is that okay? And what is your W hat ML? So I am actually defining another estimator, which is xx transpose, which is actually is this one, xx transpose plus lambda I inverse xy. And what is W at ml? It was this, right? Correct.
Yes, sir.
This part is clear, right? Now, will this be a this is another matrix, right? Right? How does it will look like? Let us just give me a minute. I'll just plug in that charger. Just give me 2 minutes. Okay. So until this part is okay, let us say, and how this matrix will look like. Okay. So A is, let's say, matrix like this. A, B, C, and D. Some values. Now, how this A plus lambda I will look like? It will look like this, right? A plus lambda, B, C, and D plus lambda, right? Because I is your identity matrix 1 0 0 1, and if I multiply with lambda, this will become lambda 0 0 lambda. Is that right? Am I audible?
Yes, sir.
Okay. Is that okay till now?
Yes, sir.
So what will be the trace of this matrix? A plus lambda A. It is A plus lambda plus B plus lambda, right? Hmm?
Yes, sir.
I say that A plus B plus 2 lambda, right? Like that, right? So,
Sir, D, it should be D.
hmm?
So D plus lambda.
Okay, D plus lambda, right? Or whatever. This is fine, right?
Yes, sir.
And that should be equal to that should be so that means you can see that all of this.
Actually, I lost the voice. What happened? There's two lines after the matrix. This one.
So okay, this is the matrix, right? A plus lambda I. This will look like
Yeah.
this, right? A plus
Yeah.
lambda D plus
Yeah.
lambda.
It is okay. It is okay.
And then you see that the trace of the matrix will contain that lambda value right there.
Yeah.
Yes, sir.
A plus 2 lambda.
Correct. So
And
now
multiplied by the dimension.
right. So similarly, if I wanted to find out the eigenvalues of this, right? Eigenvalues of this matrix, X transpose matrix, what they will look like now? D times actually. So actually, if you think of this as this is two dimensions, right? So it is D times lambda, right? That will actually translate into the eigenvalues also. So whatever you are actually adding that lambda there, how will I show that, right? Suppose A is having the eigenvalues of, okay, so what, let's say A is having eigenvalues of lambda 1 and lambda 2. What are the eigenvalues of uh, A plus Ci? I hope you remember this. It is
Yes, sir.
lambda 1
Lambda
plus
1 plus C
Okay.
constant.
and lambda 1
Okay.
plus
Yeah.
lambda
Lambda
2.
2 plus constant.
So
Two.
say,
Okay.
right. So when I say x transpose plus lambda I, and what are the eigenvalues of x transpose where, or x transpose inverse where they were 1 upon lambda 1,
1.
1
Yeah.
upon lambda 2, and up to 1 upon lambda d, right?
Yeah.
So now what are the eigenvalues of x transpose plus lambda I inverse? Can they not be 1 upon lambda 1 plus lambda, 1 upon lambda 2 plus
Yes,
lambda,
sir.
and up to 1 upon lambda d plus lambda?
Yeah. It
Lambda.
will be like,
Right?
yeah.
So in that case, if I wanted to find out the trace of the matrix, which is equal to what? The sum of eigenvalues,
The sum of the eigenvalues.
right? So that sum of the eigenvalues will look like what? Sum of the eigenvalues will be I equal to 1 to d
D.
Eigenvalues of X transpose or X transpose inverse.
x transpose plus lambda inverse.
Lambda inverse.
Yeah. Okay.
That is equal to what? 1
Lambda
upon
I plus lambda.
lambda I plus lambda, right?
Sum is, yeah.
You can actually do it and you will get it the same thing.
Yeah. It is okay. It is okay.
And that should be equal to trace of
X transpose plus lambda.
X transpose plus lambda I
inverse, right?
inverse.
So now if I use this estimator, the W hat new estimator,
One question here.
Ah.
What was the need to add this lambda I in this X transpose lambda I?
yeah. So
What was
basically, yeah, we said no, we wanted to decrease this variance, right?
Variance.
Okay. The purposely we have done it. We
Correct,
want
na?
to decrease the value. Correct. Okay.
Give me
Okay.
2 minutes. Give me 2 minutes. I'll
Okay.
come. Okay. Is that okay? And I think we are now understood, right? Like what is the purpose of it? So what we are able to achieve here is the expectation between, let's say, W new minus W, right? Or W hat new rather. Okay. There is some problem with my tab. Is equal to O square is equal to sigma square summation of I equal to 1 to D 1 upon lambda I plus lambda, and if lambda is some positive constant, then this is going to be reduced, right? So
Reduced.
I need to find out that lambda, right, which will reduce my
Variance.
variance, or here I'll say that mean squared error between
Mean square error.
W hat ml, right?
New.
New, or like, let's say W hat ml. Is that okay?
Yes, sir.
Yeah.
I hope now it is clear. Like, I think all of you watched lectures, but maybe it is sometimes possible that you might not be able to understand
Yeah.
it.
In the lecture, it was not clear.
Right, so this is existence. So there is one existence theorem. It says it's like informal theorem. So it, what is it says? There will exist some
Which theorem? Which theorem?
existence theorem.
Existence theorem.
So what does it say is there exists some lambda, right? So this lambda, there exists some lambda, which will what? Give me
Reduce the mean squared error.
Reduce the mean square error.
which means squared error? This one, right?
WM.
Correct, right?
Yes,
Yeah.
sir.
W hat ml.
So now this lambda which you have introduced, can you tell me it's a variable of uh, or can you say that it's like observed variable or unobserved variable or latent variable?
Latent.
Latent variable, right? So observed
Yeah.
variable are those variables which you have which actually we observed from the data. Like for example, if you find out its distribution, we know that these are the parameters of that distributions. They are called as the observed variables. Those variables we introduce it and or we do not observe it through the data. They are called as the unobserved variables. So in this case, this lambda here is what? A latent variable, right?
Yeah. Yeah. Yeah.
Clear. So now this lambda actually is calculated by using the cross validation technique. Okay, the cross validation method, we find out the lambda. Okay, what does this cross validation technique is? So generally, if you understand about the data, is like in supervised learning case or unsupervised also, but you have some data, right, on which you train the model, correct?
Yeah.
Correct. In this case, let's say linear regression case, which is the model? What is the model you train? So do you know the meaning of model? It's a,
Yeah.
like it
Model.
is a mathematical model, right?
Yeah. Mathematical
Yes, sir.
model. The function.
Huh.
Some function which
Correct.
gives the level. That is
Correct.
model.
Correct. So which one is the model in this linear regression case?
This is sigma square 1 by
No. Sigma square. No. The model for linear regression. It is y minus w
So
transpose x.
W transpose X minus Y.
Okay. W, yeah, W transpose X minus Y. That is error.
That
Error.
squared error there. That is your
Objective function, right?
Is to
that is
minimize that.
that is the model, right? So that is a model for linear regression. Now you
Correct.
understand that part.
Yeah.
So that model you generally find it out from what? There are two types of data we generally encounter is training data and test data.
Validation.
Validation we'll see about now, but there is
Okay.
like generally is train data and the test data, right?
And test. Yeah. Yeah.
So that means you try to like whatever you y minus w transpose x or this, right, this error you try to uh, minimize based on what, the training data, right, and once you train this model, then you whatever the model you got, like whatever the w star you get, right, by using that w star or that model, you use that on the test data to predict the values, correct, right?
Yeah.
Right, but let us say your data is biased in the sense, or you are not able to, so whatever the randomly selected data it is there, it might not actually take all the things into account, and what on that data itself you are trying to actually generalize, right? So there is terminology called generalization. So basically uh, I don't know like whether I can introduce that part here or not, but let us say okay, I'll not introduce that here, but okay, bias and variance, okay, maybe I'll just touch upon that, but okay, again it is not the part of our syllabus, but let's see. I hope you know that the training error, right? So as you see the more number of examples, let's say number of training data, right? Okay, again, this is like not only validation, like this is not only related to training data. Also, it is actually there is another term called as a model complexity. Model complexity means like if you use a linear model or use the polynomial model, that way also you can actually think of the bias variance. But here, if you increase the number of training data, what will happen? Your training error will reduce or it will increase. Let us say you have only one training data, and then you have 100, and then you have 1000. What do you think for what, like for whatever data, the error will be lesser?
So
Training
more data means less error.
less error, right? Because you have like more examples to see and
And learn from.
fit, right? Yeah, learn from. So as you increase the number of training examples, this error will go decreasing, right? So this is called as a training error. Okay, this is called as a training error. Okay, if you don't understand at this point, it's fine. Okay, it's like it's not there into syllabus, so possibly you might not know. But there is another like uh, test error, right? So as so again, see, if you have only 10 data points to test, right? So will the error will be higher, or will the error become higher when the number of training examples are, or number of test data points are higher? So basically, this is
Error will be less when that number
test
of
data.
test data are more.
Correct, right? Yeah.
Inversely proportional. Both are inversely proportional.
Right, no, because as you see different test data points, that is not true like every time, but majorly it is true. Okay, so this is called as a test error. Okay, sorry, I think I am doing some mistake here. Okay, I think it will be like this. Okay, like this. So training error, initially it might be test error, it might be larger, again it will become lower, and again it will become higher. This is actually test error, right? Because for some it might give, because the number of training examples are also less, and the number of test examples are also less. In that case, you might not be actually getting the good results, right? Let's say you have only 5 data points for training and only 5 data points for testing, then definitely both the errors will be higher, right? Huh?
Yes, sir. Basically, we can say that the more the number of examples increases, the variance between them also
Yeah,
increases.
so this is actually is called as a variance. Okay, it's a variance, and this is the bias actually. Okay, but again, as I was saying, that it is not the part of your syllabus. If you are interested, you can actually look at this, because this is a very important concept, which is called as bias variance trade-off. Uh, you can check it out. But so the what I'm trying to say is, if you don't see the data, test error is the unseen data, right?
Yes, sir.
Unseen data means we are not actually seeing that while training my model, right? So there are maybe some outliers over which we might not perform well, right? By
Yes.
using this training error. So what we do is we don't so, and again, whatever data we are getting, we don't know how that data looks like. So what you can do is you, so this is like training data, right? My entire training data. So you use that 80% of this training data. Let's say you can actually use whatever, like 70, 30, 40, 60, like that. But uh, let us say 80% of the data. This is like majorly people use this part, 80-20. So 80% of this training data, you train your model onto this. Okay. Okay.
Yeah.
And now in the remaining data, right, you try to test and check where now what will happen is, this 20% of data we haven't seen, correct, right? Huh?
Yeah.
We haven't seen this 20% of the data. That means now you are able to generalize your model well, right? Because now while training itself, you can understand that only if I do it on 80% of the data, how my model, right, is performing on the remaining 20% of the data. If it performs well, then it's good. If it doesn't perform well, then that means there is some issues in this data,
Outliers and all that.
right? Yeah, outliers are there. So now this is called as the validation set. But let's say someone will say that this 20% of the data, right, this might not be like a representation of the remaining 80% of the data. So how can I just say that only based on this 20% of the data I'm not doing proper generalization, right? So what do you do instead of that? There is a term called k-fold cross-validation.
K-fold process.
K-fold cross-validation. K you decide it manually, fine. As you do it in the k-means clustering, right? You how many centroids you need, you try it out, right? So you just try it out for that. So k is called as a hyperparameter here, right? Okay, just listen to this, okay? I know maybe this is not you have heard previously. Some of you might have heard, but some of you might not. Just to like you should get some idea about all of this, I'm just writing it down. This is, let's say, hyperparameter. So hyperparameter generally you find it out by doing trial and error method, right? So I think in the k means also we have seen that elbow method, right? You choose k equal to 1, you choose k equal to 2, you choose k equal to 3, and you choose k equal to n. And in that case that graph was like this, right? I hope you remember that graph goes like this, sub, right? And at n equal k equal to n, the error was actually 0, right? And we started with k equal to 1, but we don't need that k equal to 1 where error is 0, because that will be like so overfitting, right? So you choose where the elbow is there, right? So after that actually the uh, error was becoming like lower and lower, lesser and lesser, right? Okay, I hope you remember all of that. That same you can actually use for this. But okay, how it will work? That I'll tell you. Uh, in that case, what you do is, first of all, let's say k equal to 5. When I say k equal to 5, I will put this data, let's say, as a validation data, and this remaining data as the in the first. This is my first fold, for example. Okay, so this is my 20% of the data as validation data, and remaining 80% as the test data. Is okay?
Yeah.
Now in the second fold, so let's say this is my second fold. The second one. In that case, this is my validation data. This is the validation one. And what will be the training data now?
The rest one.
Yeah. So basically this one and this one, right?
Yeah.
This is so when you have so like that you do like I'll try to show you one.
We got that.
Got right?
Yeah. We're just changing the validation data, and other rest one is tested.
Right. And what you do then, you find out the validation errors and the training errors, right? And you after that you choose only that one which gives me the
Least
low
validation error.
Least error.
right? So least validation error and least training error as well, right? Both will have to look into, right? So the training error might not be least, but the validation error has to be the least. Correct, right? And this way, actually, you are picking what? The lambda. Okay. So, what was that lambda here? That value which actually minimizes my this quantity.
MSE.
Right.
Mean square.
ML minus W.
Yeah. W transpose X minus Y.
Whole square. Yes.
Yeah. WML minus W.
So ML actually here it is maybe I can say it is new, right? And
L2 norm of the error, expectation of the L2 norm of the error, right?
yes, right? Is it okay?
Yeah.
Yes, sir.
So this is the by cross validation technique. You choose the lambda here. Okay, that lambda, and what will it do? It will reduce this quantity, the mean squared error.
So basically, this is that existence theorem.
Yeah, so existence theorem says that there exists some lambda, because see, every time you do this cross validations, right, you'll get some different lambdas, and what we are saying is that should be one lambda available which actually reduce this part. Correct, right? Not every lambda is going to reduce this mean squared error. Why I'm telling you is that again, I said to you, right,
Yes,
as
sir, it can vary
yeah,
because
but
it is random.
yeah, but let's say if I use this W new, what is W new? It was this, right, x6 transpose plus lambda I
Lambda I.
inverse
Lambda I. Yes.
xy, right? This was
Yes.
the this was my estimator, correct, right? This was my
Yeah.
estimator. Now suppose, but is this a biased unbiased estimator?
No,
No, right?
No, sir.
But the
it
W
is
hat
not.
ML was the, yeah, W hat ML was the unbiased estimator,
Bias
right?
estimate.
Hmm.
I say that
Yes, sir.
MSc was equal to what? Bias square plus the variance.
Variance.
So in case of W hat ML, uh, that MSc was equal to the variance, right? But the bias was zero, right? Correct. But now in case of when I use this W hat new lambda, or sorry, W hat new, in that case there will be some bias associated with, right? Let us say,
Okay, in the previous case, it was this bias was zero,
yeah,
so MSC was equal to the variance. But here,
yes,
variance is not like that, right?
yeah, but it is C, some bias is there. So bias square will be
Constant.
some constant, let's
Yes,
say,
some
and
constant will
plus
be
the
there.
variance. So now both these quantities, right,
Hmm.
they combinedly should be lower
Equal
than
to the mean squared error.
the this quantity here, right? So I should get that lambda, right? I should get that lambda which will minimizes this, and that is what existence theorem said. You will get that lambda. Some lambda there exists always, or there exists some lambda which will give me this quantity. For every lambda, do I get? No, because let's say this quantity is getting lower than this, right? But this quantity has some significant right, so some significant portion which actually overturn this to this, right? So not for every lambda we are going to get that. I hope you understand this concept here.
This quantity, the MSM is less than the variance.
uh,
Now, what
let's
is the actual theorem? What is this?
okay,
Which one should be less?
okay, yeah, I'll tell you. Okay.
Yes.
Write it down. Two quantities, I'll write it down.
One is the ML, W hat ML, variance of that, right?
Let us say W hat ML
Yeah,
minus, let's say, W square
yeah. This is MSC.
expectation. What is this?
MSc of WML.
MSc of WML, right?
Yeah, MSC of WML.
Is equal to, let's say, bias square, which is 0, plus
Yeah, yeah, no bias. Yeah,
variance is sigma square into summation of I equal to 1 to
D lambda,
lambda I.
lambda,
Okay.
lambda I. Yes,
And there is this expectation of W new hat
hat
minus W
minus W
is equal to,
C plus,
yeah, okay, let's say
yeah,
C, or bias square, right?
bias. Yeah, bias.
Bias square, basically.
Positive for taking positive thing, right? Now bias square we are
Okay,
taking.
yeah, it should be constant positive, right? It
Yeah,
is the square of it.
yeah, positive constant. Yeah,
So C plus the
lambda
variance.
square
C is sigma
dot
square summation of I
I
equal
to
to
D
1 to 3
1 plus
and
lambda I plus
1
lambda.
upon lambda I plus lambda. So
Yeah,
existence theorem says that there exists some lambda which will give me this quantity less than
Okay, got it. Previous one. And then we will iterate it again and again and we'll get it right.
Yeah, but not every lambda you will get it, right? Because
Only one,
because
only one lambda will be there which will get the less
I don't know
relation.
one, but yeah, there exists some lambda. It's kind of like
Yeah,
that.
and that is the latest lambda.
So
Latent
can't we
lambda.
take it like that, the mean squared problem where there is only one global optimum?
Yes, you can think of that, right? So yeah, that is correct, because that is, again, it's a parabolic problem, so you'll get anyway one solution will be there. But do you understand the importance of this is what, like, I'm introducing some lambda here to what, to reduce the variance. But in when I try to reduce the variance, what will happen? Bias might
So bias
increase,
is
right?
introduced.
Bias is introduced, bias is increased, right? Because it was zero previously, now it is introduced there. So if I pick that lambda which actually reduces this variance like drastically, still it will not be useful, right? Because in that case the bias is going to be increasing. So if you understand that underfitting and the overfitting problem, right? If the bias
Yes,
is
sir.
high, what will happen? Underfitting.
Overfitting.
Underfitting, right? uh, I think when the variance is higher, then the overfitting will happen, right? Okay, think of it like, and then
Okay, okay.
see that. But is it fine? Is it
Yeah,
understandable?
Yes, sir.
yeah. Now it is
Okay, now
something.
we are moving to the concept of, let's say, ridge regression. I'll and okay, this concept actually is basically based on whatever we have discussed. So that means what I wanted to find out is that lambda, right? Till now, I just said that okay, cross validation and all, what you do, but there is another uh, aspect to it, is what, there is like, if you introduce some prior here, what will happen now? So until now, what we are doing is we are finding out the maximum likelihood estimate, right? Correct, for parameter estimation, right? See, we said that there is some w hat nu, right?
Yeah.
And which is not w hat ml, correct? But I just said to you that I'm just adding lambda to this, right? Correct, right? I said this is a solution, correct, right? To achieve that whatever we have discussed till now. But how to get this part, that is a question, right? uh, I should know that how to find, anyway it's the estimate, right? I know how to find out w at ml, how to find it out by using the maximum likelihood estimator, right?
Maximum
Okay,
like.
or maximum likelihood. But how to find out this, I didn't say about it till now, right? So this is actually finding, we can find out this estimator by using the Bayesian modeling.
Bayesian model.
What is, I think we have learned about that Bayesian estimator. If you remember, what was that Bayesian estimator was saying? So basically, your
The
estimator,
posterior distribution
yeah. So the posterior distribution is
Proportional
directly
to the
proportional
prior.
to
Prior
proportional to
like
the
prior
maximum
into
likelihood and the prior distribution.
not maximum likelihood and the prior, right?
prior divided by evidence.
Evidence is actually constant, so because it's a
Yeah.
normalization thing. So I hope this you remember, right? Okay. Now what to do? And I again will think about this. What was the likelihood problem? It was the problem of like this: the y given x is normally distributed with w transpose x sigma square, right? This was the distribution for. Okay, now think of this sigma square as 1. You can actually use that sigma square equal to sigma, like keep it as sigma square and you solve it. But now for simplification of this terms, right, it's again, it is not very difficult, but for right now you just think of this as 1. Okay, that means I'm saying that there's variance of 1 here. Okay, now uh, until now I was, whenever I was doing that maximum likelihood estimator, that time what I was saying is that I do not have any information about the w, right? W actually I was treating constant, right?
Yes.
Correct. And that's why, because you, if you remember it, it is like this problem we tried to solve. It was a function of W, and we treat W as like, it's not, we were not treating it as a variable, rather we were treating as a constant, and we are saying that f dash of W is 2 times y minus W transpose x into x, right? Let's say, okay, W transpose x, or simply I will say that Wx, and then you got that solution, and then equated to 0, and then subsequently you found out the solution to that.
Yeah, yeah.
But now what I'm saying is, this W, I know from the prior experience that this W is having some distribution, right? W is a random variable with, let's say, and this distribution is normal distribution with 0 and some variance gamma square I. Okay, right? This W is in how many dimensions? RD, right?
What
And
is this gamma square I?
variance. Or
Okay, some
I can say that,
assume.
okay, this is actually, if I think of this W as in RD, it will be a covariance matrix. We are saying that we have some prior information about this, and actually this is a conjugate pair, right? Conjugate prior. I It's okay if you remember conjugate prior, it's fine. If you don't, it's fine. Conjugate priors are basically those, if you use that, say, prior as normal, right? Its posterior also will be a normal
with the
distribution,
same distribution.
right?
Same distribution. Posterior and prior will have the same
Same
distribution.
distribution. That is what that pair is called as a conjugate prior pair.
Okay.
And now, basically, what is your posterior? Is this, right? X1, Y1, X2, sorry, Xn, Yn, right? Given the data, what is the W, right? That is the problem we try to solve. And what actually it is probability of X1, Y1. I hope all of you know this Bayesian formula, and x2 y2 and 2xn yn, and times the, what, times the,
Probability of W.
which is the prior. So can you tell me what is this part? What is the probability of, okay, this is a joint density, right? Because we know
Yes,
that
sir.
x1, x2, all these data points, actually they are IID distributions. So what are the, and how this, okay, okay, can you tell me probability of x1 y1? The joint density is nothing but probability of y given x into y, right? Is that okay? Mm, okay, fine. Don't worry about it. Let us not worry about it. I'll just directly write down this probability is basically the joint density, how these labels are generated, and uh, these labels were generated like this, right? When x is normally distributed with W transpose x and y. And when I find out its density, basically it was e to the power minus y minus 2x upon what? 2 sigma square, but sigma is basically equal to 1, right? I said 1. Is that okay? This distribution is fine.
Yes, sir.
But this is, we are doing it for uh, all number of examples, right? So I equals to 1 to n, right? Hmm? Is for all data
Pi
points.
is the product, na?
Yeah, this is a product, right? Pi is a
Okay.
product.
Okay.
And what about this distribution I said? What is the distribution of W? It is normally distributed with 0 gamma square I. So what will be the prior probability? So this was, okay, this W was in RD, right? So this will be like this matrix, right? 0 0 vector. This is a vector of d dimensions, and this is a covariance matrix. How it will look like? Gamma square
D cross D.
1 gamma square 2 gamma square, and like that, and gamma d square, right? So
Yes.
for each w1, what will be the so okay, basically what I'm trying to say is this is a product, right? Again, probability is a product of I equal to 1 to how many d, right? Because this w I said is a vector which is w1 w2 up to wd, and that is simply it is mean 0 and it's variance as gamma square. Done. Okay, again, all of these w's we are considering as independent of each other, IID. Now in that case this will be e to the power some sigma square will be there, but we are ignoring that.
This was not getting here. What is this? It is a d by I. I'm not getting this. The second part.
Pi product.
The product. Okay. The product of this.
Each w's, right? So w1 is what? What is the probability of getting w1? It is e to the power minus w1 square, or sorry, w1 minus 0 square upon 2 gamma square, and here it is 1 upon root 2 pi gamma, right? Basically.
W1 is the estimator, na prior estimator.
No. W1
What
is
is?
like okay. Okay. I just said no. It's W is some prior.
Yeah.
So W it will be in d dimensions, na?
Yeah. The in diagonal.
D dimensions. What do you mean by W is in d dimensions? This one. I wanted to say okay. Each xi is in d dimensions, right?
Yeah. Yeah.
So each xi, how will I write that? It is like let's say x11, x12 up to x1d, right? D
Yeah.
feature.
Yeah. Yeah.
And when I have W, it is like W1, W2 up to WD.
WD.
Right?
WD.
Right?
Yes.
Then only I'll
Yes.
get YI. So
Correct.
each of this label is YI is equal to what? W1 X11 plus
That's good.
W2 X12 plus like that
Yeah.
WD.
Linear combination. Yes.
So each of the label is the linear combination of this. But then
Correct.
how many parameters do we have? Like D parameters, right? W1,
D
W2.
parameter. D parameter.
Three parameters, and
Yes.
what I'm saying is each of this parameter w is actually normal distributed with
Okay.
so
Each of this.
and I see I think MLF we have that concept of
Hmm.
joint normal distribution or multivariate normal, bivariate normal, if you
Yeah.
remember.
It was. Yeah. It was that. But.
Uh, so that bivariate normal concept is there. So with that
Mhm.
bivariate concept, right? Bivariate normal, because each of W I am saying that is a normal. Okay, so each of Wi is normally distributed with mean 0 and
Variance.
variance gamma square. Then in
Gamma.
that case, the joint density of W, which is like uh, if I write down, like if I write all of these W's into a vector, it will be W1 W2 up to WD, correct? So the joint density of them is basically what? It is this product of I equal to 1 to D
Product of I want to D.
e to the power minus uh,
Mhm.
Wi square minus mu
My
square
message mu square. 0. Yeah.
square and
2 to 2 sigma square.
root
Gamma
2
square.
pi to the power
Correct.
D
Correct.
to uh, I think root 2 sigma, right?
2 pi sigma.
But see, this is constant, right? So we are ignoring that part while
Yeah.
considering it to the,
Yeah.
because in posterior we are actually not worrying about the, because we are saying that it is proportional to that. In the
Yeah.
proportionality sign, when we introduce, we don't worry about the.
Yeah. Yeah. Yeah.
So
Hmm.
now this posterior will become how it will look like. Now I'll just write it down. So pi equals to I equals to 1 to n e to the power minus xi minus what is it? Sorry, not xi, yi minus, right?
yi minus
Yes.
w
W transpose xi
transpose xi.
upon
Yes.
2 sigma square, and sigma square I
Sigma,
said is 1
sigma is 1 to 2
into this prior, which is pi equal to
into 1 I to d
e to the power minus wi
minus
square upon
half
2 gamma square, right?
2 gamma square. Yes.
So
Correct.
basically, if you think of this, right, this quantity, so it's a product of this, right? Can I write it down like this: e to the power minus length of this w vector
Mm-hmm.
2 gamma square. Is that okay?
Yes. Yes. Yes.
This entire product I'm writing it as like this. Is it possible, right? Yes,
Yeah. Yeah. Yeah.
because okay, e equal to minus w1 square by 2 into e to the power minus w2 square by 2 into e to the power minus w3 by 2. So what is the product of this? It is basically it is sum, e to the power minus sum of I
2d
1 to 3. In this case it is
3.
w1 square plus w, or
Yeah.
rather if I
Correct.
right, it's wi square by 2.
Yeah. 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 Correct.
Basically if I think of this as, right, it's a length of that wi minus 0 vector basically. Correct?
Mm-hmm. Correct.
Okay, so and that way I'm writing it like this. Okay, what will happen now?
Mm-hmm.
And this is called a maximum a posteriori. Okay, so this probability of this posterior distribution is probability of, let's say, w given the data, right? Okay,
Given t.
now what I need to do, I need to maximize this likelihood, right? Now, and
Yeah.
this whatever you get, right, that you initially I said about it is as mw hat new, right? Now I'm just giving it as a name instead of new. It's called as a map, which is a maximum a posteriori uh, distribute or estimator, right?
Mm.
Which is arg max over w and summing over this, right? Summing over what? Again I'm taking the log likelihood, right? If I take a log likelihood, what will happen then here? This product will become
Minus half
sum of I equal to 1 to n, let's say minus half, and
yi minus w transpose.
transpose xi, or okay, that square will also,
Yeah, we'll also.
square it will be there. Okay. Until now I didn't do that minimization, and
Yeah, yeah.
this will become minus, or whether I will say that
Minus half
sorry,
wi square upon to
right, so
minus half
yeah,
wi square
minus,
divided by gamma square.
yeah, square by 2, right?
Yeah, yeah, correct.
And 2 gamma square, right? That is also there,
Gamma square.
right? This is okay.
Yeah, yeah.
So if I take minus sign common, if I take minus sign common, what will happen?
Minus half we can take from.
Minus half, or I'll say that, let's say minus also. This
Hmm.
problem will become the minimization.
Summation. Summation. Yeah.
Summation is already there. Yeah, but yeah, sum of all, and that I can say that R min over W. I think it was 1 by 2 summation of I equal to 1 to n yi minus W transpose xi square
Plus
plus half, right,
half
W square by 2
2
gamma.
gamma square.
Okay,
Yeah.
now what we'll have to do, we'll have to find out its
Dif-
gradient, right?
differentiate. Yeah.
Differentiate and equate to 0. So is del f of w will be what? Is a function of w, right?
Yeah.
Now I say it is a function of w, and this function of w will be what now? Put it down. It is x6 transpose w minus xy. It is easier. You can actually find it out from here also. Plus w by gamma square. It is not difficult because if you think right,
Yeah, it is a standard 2x equal w minus 2xy. Yeah.
that we are equating it to 0, and now whatever the estimator we get, that is called as map estimator. That is equal to x6 transpose, sorry, x6 transpose plus, what will happen now? You tell me. So this, see, this quantity and this quantity and this quantity will be added. Xy will go to that side, correct? And correct, right?
Xy divided by
Divided, it will not happen because it's a matrix. So we'll have to take the inverse.
okay
1
inverse.
by mu square.
Yeah, x transpose 1 by gamma square I. What is
Because
how?
to get that matrix format, right?
Okay, formatted. Yeah,
Because
got it.
it's
Got it.
right? Everywhere it is there, so it is.
It is just equivalent to that x transpose pseudo inverse. Just we added 1 by gamma square I, right?
If you remember that, it was like this, no? W hat was lambda I
Correct.
inverse xy, right? But
And
this
this
lambda,
lambda is equivalent to 1 by gamma square.
yes, right? And this gamma square we can find it by using what? Cross validation.
Correct.
This was what? This was we thought of, right? We say that okay, if I can find out that lambda, I'm able to reduce the variance, right?
Correct.
But there should be some way, right, to find out this quantity also, W nu, and that is this basically, right?
No,
And for that, okay, to get it, what have new thing which new thing we have added here? Prior.
prior.
And what was the distribution of prior? Normal, mean 0, variance square, right?
Yes, sir.
Yes.
So this quantity which I have written here, can I say that now? Okay, now by analogy, I said that lambda is equal to what? 1 upon gamma square.
Yeah.
Yes, sir.
Now this, can I write this is in a different way by saying that it is
Lambda.
Half of lambda.
or by 2, right? So let's say let us not worry about this 2 now. Okay, this argument of minimizing W over this, what it is called? It is called as a ridge regression. Okay.
This is for ridge regression.
Okay, what we are doing is we are enforcing that some lambda here, and now if you think of it clearly, uh, if my weights are like too large, right? If my weights are too large, okay, what do you mean by weights are too large? Okay, each of this label is, we thought of each of this label as what? W1 x1 plus W2 x2 plus WD xd, right?
W is the weight.
Right? And if the weights are higher, what does that mean? This feature will get the more importance, right?
Yes, sir.
Yeah.
Right? So if your W's are greater, what does it mean? Your features are getting actually more weight. So that those features are actually becoming very important. And when we try to minimize this, what will happen? Only the regression problem, when we try to minimize, uh, definitely that you actually you are end up in giving much of the, you know, okay, what word I used, I forgot. uh, I think I used that word, importance, right? So you are actually giving the importance to, not equal importance, but importance to majorly every feature, right? Correct? Right? Now, what does that mean in understanding? Let's say, so the sir has taken one example, right? So there is, let's say, height and weight. These are the two features, and there is another feature which is called 2 height plus weight. Okay, this is f1, this is f2, and 3 features. So if you just try to solve the normal linear regression problem, you will end up giving the importance to this plus this and plus this, right? But ideally, we should give the less importance or zero importance to this, right?
Yes, sir.
because see, it's a redundant feature, right? It's like if my y is dependent on height and weight, uh, uh, basically this is also translating the same thing, right? Okay, your y is
Yes,
dependent
sir.
on,
It can be expressed as a combination of the first two features.
right? So why we need that, right? So in linear regression, actually you are giving some importance to that. Let's say we are actually not discarding any of this, right? So if I discard here, if I give the more importance to, let's say, here and here, can I get the solution to this problem? Here weight is there, where height and weight are there. That's also okay, right? It's fine, right? If I give weightage here and discard this, still I get that, right? The only thing what will happen is, maybe this c1 includes, like, let's say it is 2 and it is 3. What happens, instead of giving the equal weightages, see, still I'm saying that we are not actually giving equal weightages to every feature, but for understanding purpose, let's say we have given some weightages. That means I'm saying that equal weightages we are given. uh, but if I give more weightage to these two, I'm able to solve that problem. More weightage, let's say here 3 and 4, and I'm going to give it 0. So what will happen here is, I am actually reducing the features, right? Because let's say your y is what? Sorry, uh, y is what? Let's say y was this, uh, 3 height plus 4 weight. So how will I get 3 height plus 4 weight? 1 plus 2. Okay, one height plus 2 heights. How many heights? 3 heights, correct, right? And 4 means, let's say here we are saying that 2.
So the last one we can use?
Huh?
The last row?
No, you can use anything. See, but which will be the better solution, or will that give me the better answer, right? So that also is important. So here, uh, 0 height. So how many?
One weight. One. No,
One weight,
two,
or
two,
let's
two.
say 2 weights, and here
One.
2 height. Okay.
Two is already there.
Okay. So let's say
One
1.5.
more height.
1.5, right? Because I need y is actually this, right? 3 height plus 4 weight. This is my problem, right? 3 height plus 4 weight is y. And if I give some weightages here, so it is like 3 height, 4 weights, and 0. Fine. Is that correct? So basically, I'm trying to regularize this, right? Weights. If I include this term here, what will happen? If your weights goes too high, right? This problem is the minimization problem, right? You're trying to minimize the weight. So uh, if the weights are 0, what will happen then? All weights are 0.
So weight is
Okay, maybe we'll discuss that, maybe some more time, some other.
no,
Okay.
so weight is W here.
Huh?
Weight is W here.
Weight is,
W.
yes, w.
So if weight is zero, that will you asking.
Okay, so what I'm saying is it possible to get all weights 0 in this case?
So if weight is zero, then it will be
Okay.
already.
Yeah, okay, I understand the problem. Okay. Okay, let us say, okay, my point is to, let's say, argument, I'm just doing that argument that I wanted to minimize this. So if I wanted, what this actually enforce me is this called as a regularizer, right? What it does is, we should not give the higher weightages to unnecessary, or let's say, or not higher weightages to the uh, required, like the features. Suppose, let's say, okay, how will I tell you is that there's like very good concept about this, but okay, maybe I'll not able to explain it here. Okay, sometime I'll explain it. So okay, for example, right now,
Next in the next session discuss.
yeah, I'll sometimes I'll just brought it up, because right now I think this is all you are gathering into your head, right? I think at least sufficient right
we
now.
will go. Yeah. Now we will be able to grasp the lecture, because I went through that, but I was not getting that. But now I think I will be able to do that.
So this was the problem, right? Regression problem, which is summation of I equal to 1 to n w transpose x I minus yi square, correct, plus lambda w square, right? So that's the problem, and this is called as the regularization term. Regularization. It's like very important concept again. Regularization. Again, if whenever you go ahead, also, what is w here is this w. Norm of w is summation of I equal to 1 to d, right? Is that okay? Is that okay? Hmm? So basically what you are trying to do here is you are actually trying to put that lambda there, which will what it will change the solution to your problem, right? So it will try to restrict your w's not to go like too far. For example, what I'm trying to say is, suppose you have w1 x1, thus w2 x2 up to wd xd, right? That is my y, right? Correct. But let's say w was for this feature, w was like too high, and for these features, the remaining features, w was very low. What does that mean? You are actually discarding the remaining features, right? You're not giving them the sufficient weights, let's say, in your problem of linear regression. What you try to do is, you that whatever the w's are going, right, like at will keep them into certain threshold. Okay, that w shouldn't go too high, right? If the w goes too high, what will happen then? Then lambda has to be minimum, right? Okay, lambda is what? 1 upon gamma square, correct, which is the prior experience. So based on that, my prior experience, uh, if that okay, it will
It's
keep,
a the balancing.
yeah, it is actually keeping that w's into certain, or it is restricting that w into uh, certain threshold, right? This is the problem of constraint optimization. Okay, so this problem can be written as this way: minimize w over d, summation of I equal to 1 to, what is it, n, right?
So it is lambda which is controlling W weight.
Correct, and that is why it is called as a regularization parameter,
Okay.
yi square. And how we are controlling that? We are saying that such that we are actually saying that this w, the length of w, right, should be within some limit. Let's say that limit is theta. This is the same problem we are actually trying to solve. So here basically lambda is actually regularizing that w's. The weight shouldn't go uh, outside certain limits, and that's why and that's how we are actually uh, getting that lambda. So this theta, whatever we have introduced, the threshold, this is called as a threshold or limit, right? This theta basically should be a parameter. It should be what? It actually depends on what? Lambda, right?
How sir?
Because see, I am equal. I've changed this. So okay, this was your original problem, right?
Yeah, we will do it in that way. Now going away.
Huh? Oh,
Okay.
okay. This is your original problem we try to solve. Now we are
Hmm.
putting some constraint over it. So this is a constraint, right, on W. This
Yes
controlling
sir.
that W. So this constraint, I'm writing it in these terms. Okay. So basically, what it is doing? This lambda is trying to, because see, this quantity is, if I increase lambda, right, then W should go low, correct, right? Or if I
Yes sir.
increase this W, then lambda should go lower, right? So that means this lambda is actually control. So if my w's go beyond some level, right, that lambda will make it down. Why? Because this problem of minimization, right? Like again, so that means the same problem I try to visualize by using, because I'm saying that it is a constraint problem. So I'm just considering that w by using this theta, right? So basically that theta should be dependent on the lambda, right?
Yeah.
Okay.
Theta is a,
Theta is kind of okay to this is for to understand the problem geometrically. This theta is what we are saying is, let's say there are two features w f1 and f2, or x1 and x2. Now, sorry, two features, let's say f1 and f2, and if you wanted to see that one data point, we are seeing into this. So these are the two what weights, right? This is a parameter space, right? We are seeing the two-dimensional parameter space.
yeah.
Two-dimensional parameter space. What we are saying that this constraint, we are keeping constraint on what? W, weight vector. What is the weight vector in this case? Square root of weight vector is what? It is W1 square plus,
W1 square plus W2 square.
right? So,
Yeah.
and when I say that it should be less than or equal to theta, right? So when I say equal to theta, this is the equation of what? Circle.
Circle.
Right. So that means, and if you are pointing it out this circle, then what will be when I say less than or equal to theta? What is the feasible region? Is the feasible region, right?
Mm.
So what I'm saying is my W and W2 should be coming from this region. Got it?
Yeah.
But the W hat ML, right? The W hat ML, which was the problem, which was the estimator for what? Original linear regression problem, right? Without the constraint.
Mm.
Is that correct?
Yes.
W hat ML. Uh, will that be inside this region, or will that be outside this? It should be outside somewhere,
It will be outside.
correct? W hat
Mm.
ML. And the mean squared error for this W hat ML will be lesser than what? So this is the lowest. So W hat
Lesser
ML
than
is
lesser
at,
than this W. This is W
yeah.
square.
So what was our objective function for linear regression? This one, right? W hat ML minus, oh sorry, xi minus yi, or yi minus this quantity square, right? This was my function of W hat ML, right? And this is the optimal solution, right? Why this was the optimal solution? This was the quadratic function, right? This is the quadratic function. This is a convex function, correct, right?
Mm. Yeah.
And if I try to solve the convex function, I will definitely get what? The minima, right? Global
Minimum.
minima. Global minima, right? So whenever you solve for the convex functions, that will be your global minima. And what does that means to say? The error occurred, or the objective function at that point is the minimum, right?
Minimum. Yeah.
So that W hat ML will have the least square, least loss. Got it?
Mm.
But when I introduce some prior, and if I try to use it the ML, right? So map estimator, in that case, the solution will lie where? Solution lie in this region, right? So whatever solution I get by using that ridge regression or solving that ridge regression problem, let us say I got, let's say this this is the solution. Let's say the error here will be lesser than this or higher than this?
Higher than.
Higher than this, right?
Yes.
Right. Definitely it has to be higher than this, because the minimum error which I am getting is
WML.
W hat ML, and this error what I am getting is actually higher than this. Is that fine?
Mm.
but I am okay to do that, because that way what I'm able to achieve, if I use this ridge regression problem, what I'm able to achieve, I'm able to get the lower variance, right, on that mean squared error of W at ML. Is that fine? Okay, you'll have to try to connect all of that, then only you'll be able to understand that.
Yeah, after going through the again lecture, the whole lecture.
Okay, so okay,
We'll do it.
fine. So I'll finish your with this concept, right, and then I'll
Yeah.
let you know, let you do that. Lasso
Yeah.
regression is the special case of this. Maybe that is like, okay. So in lasso regression, what will happen is, instead of taking that prior, so what we did for ridge regression, which prior we used, Gaussian prior we used, right?
Gaussian, yes.
So what was the prior there in the ridge regression? The prior we used for W was normal square 0 gamma square.
Gamma square.
Then I'll get the ridge regression. If I use the uh, norm 1, right? Norm 1 prior, which is what? Laplacian, actually. Laplacian norm, right? So that, like, Laplacian we use. In that case, your problem will become like this. I will not. Maybe I'll somewhere I'll discuss about these solutions and all. But for now, I'll just
We will discuss next time. Yes.
yeah. So okay, I'll just write down the lasso
Okay. Yeah. Please.
lasso regularization, right? So L1, it's called lasso, and the objective function will become like this. Similar. So it is kind of argmin over W. W transpose xi minus yi square, right, is summation of I equal to 1 to n plus lambda W. What is the change here?
Absolute value of lambda W. Here it is not the norm.
L1 now we are actually using, so
This is L1 norm.
yeah,
L1 norm means the absolute value, no?
yes, so it will be summation of I equal to 1 to d, or this term can be written as W1. 1 is to identify that it is L1 norm.
L1 norm.
Yeah,
And L1 norm means the absolute value of W.
Yes. So basically, it will be like this: square root of absolute of W1 plus absolute of W2 plus absolute of W3 until.
Why a square root? Only this.
So it will be like, if I don't take the square, right, it will be the square root only, right? No. Okay, I think no, it shouldn't be square root. Okay, it should be.
Square root should not be there. No, only.
Yeah, correct. Yeah,
Only absolute value summation.
Yeah, because we are not. Okay, I am just right.
In the L1 norm is there.
Right. Okay, it should be there, right? Fine, and W2 norm will be its L2 regularization. When I use this is called lasso, and when you use L2, it will be ridge.
Then it will be a square root, right? No?
That is square root, but then again you are taking the square of it, so it will again go away square root there.
Yeah, correct.
I think I didn't show you that how the solution comes. Maybe in the next session.
In the next session, we will discuss it again.
Yeah, probably I'll not take that session, which is on Friday.
Okay.
I'll ask Nikita to take that out.
Notes will also be available, no? This notes.
This one, huh?
Yeah.
This one, I don't know.
Not this one. What you prepare in the discourse, we will upload this week 6 also.
It will be there. It will be there.
Yeah, because this is required not to revise it.
Correct.
Because this one.
Okay, then fine.
Okay. Good night.
At least 5 people are there at it. Okay.
No, we are feeling sleepy. Good night.
Good night.
Okay. Thank you. Good night.